computational mechanics, what this field is about, and giving you some glimpses of the work that people do in industry and the application side of it, and also some bits about what goes into the conceptual framework of computational mechanics. So, computational mechanics, as you can see the title, computational mechanics, the world of simulations. Uh, Computational mechanics is a tool that is used in developing simulation technology. So, if you look at systems around us everywhere, whether they are on ground, like in automotive industry, you can see a car on the left and some wind turbine systems and gas turbine system, which is used in aeroplanes. And then even if you go further beyond in space, then we have space systems. So when it comes to the design and development of such kind of complex systems, the traditional calculation methods, which would have been like 100 years back, people were just doing pen and paper calculations, and they were using some basic equations, mathematical models to make some physics-based information, to get some physics-based information on how they can design some simpler designs. But when it comes to complex systems now, because nowadays and in today's world we are designing much more complex systems than we did in the past. So it's a challenge that how we can simulate things, because if you can simulate things virtually, you can predict that how something would look like if you design certain system in a certain way, and you put in certain materials, and it's going to be used in the in-service conditions, then depending on what loads act on it and how it is supported and all, you can predict the overall behavior of the system. And once you have this confidence that your system, if you design in a certain way, then it is going to function in such a certain way, then you can make it much more better. You can improve the designs, and you can basically come up with a system that is more robust, much more versatile, and can withstand the in-service conditions and the different constraints that act on it for a longer duration of time. So when it comes to engineering, I would like instead of going on for any complex definition, if it's simply speaking, what you do in engineering is like you have some scientific principles, physics-based mathematical models, and you are going to use them to solve real life challenges. Okay, so in the school, you would have been studying a lot about the fundamental physics, like the Newton's laws and the different equations of motions and all these things. These are at the very fundamental level. These are the base of the conceptual framework that is used, and that is then further extended to some more complex uh, theories when you study engineering. And if you study something, whether it's about solid mechanics, or even if you go into electromagnetic systems, then in all these systems, what we are using is that we are using some physics-based mathematical models, and then we use them as a our conceptual fundamental model, and then we use that into whatever design we are making. So when it comes to computational modeling, it can have application in a lot of different fields. Some of them are just mentioned here in the slides, but this no way this list is exhaustive. Like whether it's like in mechanical engineering, and if you have like a structures like bridges, buildings, and aircrafts, then these are structures. So you would want to do a structural analysis, and this is what I'm going to be mainly talking about in this presentation. But there are other things as well, like fluid dynamics. CFD is was which stands for computational fluid dynamics, used for modeling of airflows around airplane wings, or like blood flow in arteries, or like cooling systems in cars. uh, and then like vibration analysis, like for example, if you are designing some buildings which can withstand the earthquake, or even like turbines. When you're designing turbines, it can have very fast speed motion of air would sometimes lead vibrations into it, and the vibration can result in the total failure of the system. So you want to study the design for its capability to withstand some vibration forces. And if you go into other fields of engineering like electrical engineering, then if you want to design some electromagnetic system or some electronics devices, that's also a place where you would use simulation engineering. And other things like aerospace, civil, chemical, these are just a large number of applications. And I would give you a few seconds to maybe write in the chat if you can think of some applications where you would see, and I would try to explain, like for example in manufacturing or anything. If you want to write anything that you see around you, and like if you wonder that if it can be simulated, then just write in the chat box. I would give you 10 seconds to think and write, and I would explain how it can be used over there. Just you can write about anything, like any sort of product you see, or that are around you, that you see the engineering is used behind that. Well, okay, I would go ahead and start actually talking about some of the things that I could think of. And these are the ones which are also mainly used in engineering. And I will start talking about first by going a little back, a century back, when things were being designed in, for example, let's say automotive industry. People were doing a lot of design on paper, and then they would go and build it, and then they would test it. So they would break the thing, and then based on whatever information they would have gathered, they would then go to the next stage, and then again design it based on the information they have from the previous stage. And they would continue this various iterations until they are satisfied with the final design, that it can withstand the whatever requirement they have. For example, if you have been recently following the news of SpaceX, they had this they were testing this rocket which went up, and when it came down, instead of splashing in the sea, they could use the mechanical clippers to capture it back, and then it can be utilized again. So this is also an iteration, like they do it in multiple stages until they have the confidence that yeah, now the design can perform in a certain way. So this is how traditionally the designing of systems always has been. Like you go through multiple iteration, you try again, and you build it, you break it. But when it had been done traditionally without any simulation, the number of iterations were very large. So using this simulation, you can save a lot of resources as well as time, and you can design new systems which are much more complex, and can provide you much more feasibility in terms of the number of products that you can make, and the this all the kind of complex scenarios that they can function in. So computational, if I talk about computational modeling, I'm going to mainly talk about computational mechanics, but to actually give you a brief overview, engineering systems that we can see around us, like they can have mechanical aspects of them, like thermal aspects and fluids. So these are the major ones that are under the umbrella of computational mechanics. And then there are some combinations as well, combinations like thermomechanical or thermofluids. And there are something and the people that do in the electrical side as well of engineering systems, they design some electromagnetic systems. So that's also a part of computational modeling. And if you take the whole thing together, then the entirety of this is it comes under multi-physics simulations. And that's also the real in reality, everything happens at the same time. All these factors are going to be working at the same time, whether it's a mechanical, thermal, fluid, or electromagnetic. But depending on the application of what you are designing, there may be one aspect that may be more predominant than the others. And that's why we just go for one analysis rather than going for the whole multi-physics simulations, because it can be computationally very expensive and may not be feasible. And also it's not really required in such cases. So why do we do computational modeling? Well, just to give you a few points. Well, you can predict, analyze complex engineering systems. You can solve problems that are very difficult or otherwise impossible to solve experimentally as well as theoretically. And you can design things in a much more optimized manner, that which will also improve the performance of your overall system. And then you can save a lot of money, because you can design things virtually, test it, break it, all things in the digital space. So you would also reduce costs that are associated with the material, the infrastructure setup, the people who would be involved in that whole thing. And you would have a better confidence in whatever system you would have designed, and that would operate much more robustly. And as I mentioned, that the real systems are multi-physics systems, but it is one or the other aspect, like mechanical or fluid, that is going to be much more predominant in its effect. So not always you go for simulating the whole physics, but rather one aspect of it. So that's why I'm going to be mainly talking about the computational mechanics. Okay. So first of all, when I said like you go for numerical modeling, you might wonder like what exactly is this numerical modeling that is involved in the simulations. So you have a mathematical model, you want to solve it using computers and not hand, but why? So I would give a simple example that I think every one of you can understand. Uh, is that if you have a quadratic equation, you must have, I'm sure you all have solved a quadratic equation, then you can find an exact solution if you have some problem like this shown on the left side of the screen. But if you go for degree 5 polynomial, and if you want to find the roots of such an equation, you don't have an exact formula for such an equation. And it's a very simple equation, because I'm saying calling it simple because when you look at the actual mathematical models that are used in solving all those multi-phase problems, they are much more complex, and you can't find the solution for them directly. So that's why we use these numerical methods that can help you in finding the solution of such problems. Just to give you a brief view of what it looks like, is like, for example, suppose if you have such a function that is shown on the screen, and you want to find the root of this function, which is like where the function would become 0. So the way the numerical methods work is that you just start with one guess, an initial guess. And what you would do is like you generally go for uh, you would just generally go for finding initial guess and then making a tangent over here, finding where it intersects with the x-axis, and then finding the value of the function at that point, and then again making a tangent over here. Then again you find where it intersects with the x-axis, find the point again on the corresponding point on the plot, and then you continue this until you have some a solution where you can see that the error that you have with the exact root, this error is less than some set tolerance. And in practical purpose, if you have some problem and you're solving uh, any real life challenge, and if you have tolerance set like something like 10 to the power minus 8, then in the real life engineering problems you are okay with such an error, and this will not affect you. So you will stop your iteration over there, because if you do not stop, you are depending on the nonlinearity of the function, you may continue doing it forever. And so yeah, depending on the what are your requirements in whatever system that you're designing, some system may have like very critical requirement of having a very high tolerance. They want to be very very close to the exact root, so you would then adjust the tolerance accordingly. So this is how the numerical methods work. Like if you have a complex mathematical function and if you want to find the solution, you use numerical methods. And this particular method is actually called as a Newton-Raphson method. uh, yeah. Okay, so now, now I would talk about some applications where you actually see it in the real life before it becomes boring if I just talk about the mathematics that is involved here. So, okay, let's look at some mechanical aspect where it is used. Well, car crash worthiness testing is one such example. On the left, like you have a real design of the system as a car, and this is a physical system. And on the right, you are shown as a virtual system in the digital space. So you would have its design done in the digital space, and then you basically throw in all the physics related concepts that you know about the material that is involved, the geometry that is involved over here in this virtual system. And then based on the computational modeling framework that you would have, the algorithms that you would have in the back end, that would determine the changes in the configuration, like how the car would look like. So you can see like there is a close resemblance between the physical and the virtual system over here. And it's possible because the physics that is there in the algorithms behind this virtual system, it's quite robust. That's why you can see it's looking quite similar. And if you can see that how the car is braking, you can imagine a lot of things, like, you can see the airbag is opening up in the left side. So you can then see the damage it would have on the passengers. You can study that, right? You can study like what the that if you are going at certain speed, like generally these tests are done at 40 miles per hour, which is like 64 kilometers per hour. So if you're going at that speed, then if your car suddenly hits an obstacle, would the passengers be safe or not? So that's one requirement that all the automobile companies have to satisfy to get the certification before they can actually launch their car in the market. So yeah, they do a lot of such studies by designing physical systems, but before that they do it virtually, so that they don't have to do it again and again by designing physically. And because if they were to do it, like, they would be so slow that in the market that the finances would not really be helpful for them, because it would take such a long time that they cannot launch their new car. So yeah, this is how the simulations helps in the this automobile industry. Um, if you can think of some other advantages in such virtual systems, just write down in the chat box, and I would describe them in more details. Um, so I would also show you like one video over here. Is like this the same test, like uh, Abacus is a software which is used for such simulation of mechanical systems. Okay, so I've just taken this video from YouTube. Uh, so yeah, you can see that when a car is hitting any, this is a rigid obstacle, which is completely fixed in this our digital space, and this car is hitting from the side, and you can see that how the car is deforming the chassis, and like, you can basically see all the different parts that are critical for safety, like this you can see the ribs over there, and this is the like the physical system of it's like, how it's going to break like. So depending on the robustness of your design, the car may handle or may not handle the damage. So you want to have that confidence in this in the overall design. So some other example is like in the same car, like if you're designing suspension system, then you would want to see like whether the suspension systems are working properly or not, like whether they can absorb the shock in the manner you want them to absorb. And if you are doing some vibration analysis, as I mentioned that in earthquake, like if you have some earthquake resistant design of some system, like in buildings, or or like turbine systems, where, as I mentioned, like you would have wind flowing at a high speed, and that would induce some vibrations because of the variations in the wind speed and the changes in the direction of the wind. So you would want to have that capability in your turbine system to withstand that vibrations. And in manufacturing as well, like nowadays, people do a lot of complex designs of manufacturing, and they need to make a new setup that is involved in the whole manufacturing process. So they would want to do a rapid design and development in the virtual space to check that whether if they were to design some dies and some cars in certain way, would it actually help them or not in producing the manufactured system or parts in a certain way. So that's where it's also utilized. And yeah, you can also have some complex contact interaction between solids. Uh, so you would also want to simulate that, because contact between different parts is a complex challenge in this computational mechanics field. And especially if also you have friction present over there, because it becomes highly nonlinear in nature. And that's what I was working like I've been working the whole time in my PhD, is like, how do I resolve this aspect of frictional contact between solids. The another example is in like gas turbine engine, for example, in aerospace. In aerospace, like the aeroplane has a lot of complex parts, but I'm just showing you one part is a gas turbine engine. So in this gas turbine engines, like these blades, they are connected over here on this. So in this central shaft. So you can see that where it is connected, it has very complex changes in the design. And when you want to simulate it, it's a simulation. It becomes challenging, because here you have suddenly changing contact zones, because it might vibrate a bit. So you want to simulate that, and it's a complex challenge over here. So like why can gas turbine engines is like how all also they look into it is like when they do a physical testing, they also every year like in Rolls-Royce, which had been actually co-sponsoring my PhD as well. They do this test, which I can show like this. Uh, Test over here is like this. They have this gas turbine engine, and whenever they come up with a new design of any new gas turbine engine, so they would simulate it by throwing some soft body to simulate bird strike scenarios. So like you can see like we just saw they just blew up a whole engine, and I can tell you that this is a very expensive test that they do whenever they come up with a new design, because they would have spent millions of pounds in this whole design, and then also breaking it. So this is how they do it. But to be able to reach that stage, they would do a lot of simulations in the virtual space before they actually go into design and do physical testing, so that they can save some money over there, and also they can come up with a better confidence in the design, and they know how things work. And this is more critical in aerospace applications, because the certification requirements for airplanes are very strict. Yeah, because it's a simple thing, like if you're flying high in the sky and something happens, you lose the public trust. Although the this honest in terms of the statistics, I can say like the more number of people die in road accidents than in aviation sector, but the public trust goes down much more faster in case of aerospace disaster than in automobile related disasters on ground. So it's much more important to design aerospace systems much more accurately, and you would use all the materials and the whole process. This all goes through a lot of scrutiny before it gets accepted. And the other thing is like for mechanical system is like, let's say you're designing a bridge. Uh, what you would do is you would do something called a stress analysis, which basically means that if you come up with any new design, you would simulate it by putting some load at different zones of it, by by taking some estimate of how much how much would be the weight of the all the vehicles and the people who would be moving through it. And this would also be a dynamic problem, because the cars and like the people, like they are going and suddenly the load is changing rapidly at some places than the others. So this is a mechanical design problem. A similar thing would be like when you go into a lift or an elevator, you must have always I remember seeing these signs which says like maximum number of people, or the weight it can withstand. So in the similar scenarios, like in the design of bridges, they would also have some weight related restrictions on how much weight can pass through the bridge. So yeah, this is one thing that's also used. The In the mechanical system, one example that I was showing previously was the testing of a car, right? So this also extends to some biomedical applications. Like if you are designing a car system that is a seating arrangement, then you would want to have this risk minimized, that is related with the collision. Like if you have this is a rear end collision, let's say your car is hit by another car from behind, then you want to predict that when the person who is sitting would get sudden jerk, would the person get injury in the neck. So you design it. So you can see like they have a model sitting, dummy model sitting over here, and they have this neck over here, which is actually represented by a spring. So they would see that based on the sudden force that the car would get from the rear end, how the person's head might move, and the sudden jerk it would get, and like whether it can lead to very high injury. So you want to minimize that risk of injury. So yeah, so you do this test for that as well before you get uh, uh, this confidence that yes, your design of the seat and the structure that is surrounding it inside the car is good enough to be used in service. Yeah. The other thing is I would want to show is a mechanical system is like a mobile phone. Nowadays, I know like everyone knows that every new year we get a new mobile phone design. Like we are getting new iPhone launched. How it's happening so fast, so rapidly? Well, it's possible because of this mechanical system designing that you do in a virtual space. So if you have a mobile phone, it would have a lot of aspects. It would have a mechanical aspects, like if you were to drop a mobile phone, they do this test, which is called a drop test. They drop a mobile phone and then see that how the different parts might break. And so they would want to have this confidence in the material that they have used. They based on the damage the mobile phone suffers, they would change the material, which would maybe use a more stronger material. Maybe they would increase the thickness of certain parts and the other. So they do a lot of such compromises in the design, because at the end of the day they want to make their system smaller, lighter, and also you would have some restrictions, or like I should say some objective you want to achieve from your design, but there are also some constraints. You cannot make it very heavy, right? Because a mobile phone, if it's very heavy, then probably it will not be a good thing. People will not want to buy it. They would want to go for something that is lighter. So you want to have the structural integrity, like it should not break up. So this is where you do a mechanical design. But then the same phone would also have a lot of aspects, like it would have some electronic chips which would get heated. So you want to do some thermal simulation so that it cools. You can design something in certain way so that it cools as well. It doesn't get heated too much. It would have some electromagnetic magnetic signals going out, and and also the receiving signals. Like whether it's about network or the Wi-Fi, Bluetooth. Okay, so these all completely together, it's a multi-physics problem. So they do all these simulations in the mobile phone in industry. And the other thing is, like, if you have some some in certain manufacturing processes, you may have different powder like things uh, which is used in like additive manufacturing. Additive manufacturing is something which is famously known as 3D printing. If you are using some certain powder, like powder sized particles, some alloys, or like some metals, if you ground them and like they become very small size, so you can use them and like use a cast, and like you can sinter them to come up with a particular shape and in a particular size. So yeah, so you can use simulations over there as well. So this one is called as discrete element method. Um Another thing is, like, in the space system, like I'm sure you must have all followed the news of space explorations and going on to Mars. So these missions are very expensive when you go for space missions. Like they cost like cost in billions, and you cannot risk to lose a lot of money without getting any results. So you would want to do a lot of simulations, a large number of simulations, before you actually go for these missions. And simulations would be very critical in this case. One more thing that is critical here is actually to get the physics correct. Um, what we have, physics, is actually a model, right? The whole physics that you have been studying so far, and that you would study further, it's a model at the end of the day. And when they do go for this space missions, they actually try to adhere to those models of physics. The actual physics may have some differences, would have some differences, because we do not know the exact reality in its perfect, and with the perfect knowledge with everything. We have these models of physics, whatever, like whether it's a Newtonian mechanics or quantum mechanics and everything that goes beyond. Uh, so yeah, they actually try to make their models as accurate as they can, and then they do a lot of such simulations so that they don't lose a lot of money. And because you cannot have a lot of iterations by sending again and again. Whenever you go for any space missions, you would want to have this confidence that it would function well. Uh, Maybe you learn something on the way, but yeah, you would want to do a lot of simulations. Okay. Yeah, this is just another simulation that I've shown, like how it works. Like in like is let's say if you have this you can see this is the Orion 3 module mounted in the heat shrink. So they do something called as finite element method, and the way it works is like you have this original design, and then you make a mesh of it. Like you take the design, and then you discretize it into a small number of elements. Sorry, large number of elements which are small in sizes, and then you put in all the physics on all those elements, and then you check how it would look like. And maybe some part of the geometry is more critical than the other. So like if some part is like going to have a very critical like zone where the you can get fracture and things may break, so you would want to have very small size elements over there so that you can capture the physics better, and that would help your analysis and you would have a better solution. Uh, yeah. Uh, Electrical, yeah, okay. So in electrical and electronics as well, they do a lot of simulations where they use these different networks and how the currents would flow. Uh, yeah, so that way they can optimize the power grids and how the electricity distribution happens, and also in renewable energy systems. That's also a network, right? And electromagnetic field simulations as well, which I would show now. Yeah. So let's say if you are designing a motor, a simple example, that's something we understand. We can clearly see that if you have a magnetic field, I'm sure like you must have in your high school studied or like would be studying this magnetic field and the different laws surrounding it. Uh, so if you have magnetic field that is cutting some metal, and if it's rotating, then that would generate electricity, and you would have this magnetic field. These are what you are seeing here is the magnetic field flux lines. So uh, yeah, when you're doing such simulations of electromagnetic simulations, then you can see the behavior of the magnets and the flow of current. So you would have lots of different parts over here, the size of the coils, the diameter, and the number of coils and how they are wrapped. So this all you can do it virtually and change the design and then simulate it again and see whether it's performing as per your desired requirements or not. Uh, okay, yeah, that's like electromagnetic field simulation. On the right, you can see the solar panel which are used in solar field. So these are also a network, right? And this is a network, and based on the orientation of the solar panels with regard to the sun, or what at particular time of the year, like throughout the year the position of the sun changes at different times of the day. You would want to better study the how you can adjust the orientation of the solar panels so that they receive the maximum sunlight, and the energy that would flow through the whole network. You can use that to predict the net energy output from your entire solar field, and similarly in wind turbines as well. So that's also one part where these electrical simulations can help you. In the electromagnetics, I was showing previously a mobile phone that was I was showing specifically for just for mechanical testing, but at the same time they also do these electromagnetic simulations. Uh, so that like if you have like Wi-Fi signals or network signals, Bluetooth signals, how the electromagnetic field would spread around it, what part would be having much more strength in the signals than the other part. Uh, and whether it's also in the safe limit or not. You also want to check that, because if it is not in the safe limit, if it's too much of a very high electromagnetic simulations are showing you that there is a very high intensity of electromagnetic signals, then that may also be harmful. So you want to also minimize that, but also make it in a way that it functions as per your requirement. Okay, let's now talk about slightly about fluids, where computational mechanics is also used for simulations. You can see, I think, the Formula One cars. Uh, so in this Formula One industry, they do a lot of these fluid mechanics simulations, where what they do is like if your car is going to be uh, speeding up at a very high velocity, then you would have the flow of air around it in a certain way. So you would want to study the flow of flow lines of air around it, because then based on that you can then see that whether your for this system would actually function in the desired manner. Like you would want to get a high speed, but you would not want the car to lift off, and you would want to maximize your performance for the fuel and the engine that you have. So that's one thing you would do using this fluid simulations. You can reduce the drag, increase downforce, and improve cooling as well. Yeah, because the engine would get hot, like the tires would also get hot. In fact, similarly, when they are making cars that we use in our daily life, That's also where they want to make the aerodynamically, they want to improve the aerodynamic efficiency, that if you are having flow lines of air in a certain way, then would it lead to the high consumption of fuel or not? So you would want to minimize that. Um, yeah, similarly in aviation sector for aeroplanes, they study that with a similar purpose, like you want to increase your speed, reduce your fuel consumption, so that it's more sustainable, both economically as well as in terms of the environment sustainability. And yeah, but the main thing that they also want to study over here is that, first of all, that it's safe for the passengers who are inside the plane, because safety is the utmost priority when it comes to aeroplane design and performance. Uh, okay, so let's just give you an example that how simulations help. Boeing 767, when it was designed in 1980s, Boeing built 77 prototype wings. But after 25 years, they had a lot of simulation powers. And this whole, like going from 1980s until like for 25 years more, like around 2000s, they reduced the number of prototype wings that they had to manufacture because they can do it virtually. So they did not have to make a lot of prototypes. Would anyone want to just make a guess? Like, if you want to make a guess, just write in the chat box. I would give you 10 seconds to make a guess how many prototypes they would have made. How many prototypes do you think they would have made? Like 60, 50, 40, 30, 10? Just write in the chat box. 59, 5, 20. Okay. Any more guesses? 50? Okay. Well, so I will reveal the answer is actually just 7. 5 was very close. So you can see the number of prototype reduction that they got. They came down from 77 to just 7. How was it possible? It was possible all because of the simulations capability that they had developed. Uh, Even now, the full, if you were to even now in today's time, 2024, if you want to design a whole aeroplane, they just cannot simulate every aspect of it at the same time, because it is so big. When you go into designing and you are going to make a mesh, like as I was showing previously, like you make a mesh using these small elements which are large, very large in numbers. So you would have, like, billions and trillions numbers of uh, uh, these elements, and it's computationally it's not possible to do it at the same time. Although we are nowadays having these supercomputers which have much more advanced capabilities than those in the past, but still it's a complex challenge, and it's going to take time, a long time, before we can actually simulate whole thing at a very high efficiency. So yeah, so they made this Boeing 787 after 25 years, and it just took them 7 prototypes. Not just it took 7 prototypes, it was 60% quieter. It was 20% more fuel efficient than what they had in 1980s. So you can see the power of simulations, right? It takes some time to do it, but you can do it much more faster than you would do otherwise. Uh, and fluids, the other thing is like wind turbine simulations. In UK, we get a lot of energy that is supplied to our homes comes from uh, wind turbines. So it's also important thing to consider. Uh, yeah, so they actually analyze the flow of air, that if air is going at certain speed in certain direction, and the designs of blade or the number of blades is in certain manner. Like, these are just a simple wind turbine that we see. There are also some other new designs as well, which you might want to Google afterwards to see that what new designs that people are making. And they are able to do that because they have this capability to simulate and see how it would look like, and the energy output you would have at the end of the day. So yeah, you have fluids here as well as the structure as well, because I was mentioning that they might also vibrate, and it's a structure at the end of the day. So you have this multi-physics simulation, right, happening at the same time. You also have these motors over here in these, right, and some and generators over there. So you would have electromagnetic thing over there. There's a mechanical structure. There's a fluids. So it's all combined is a multi-physics problem, right? So yeah, based on the flow lines of airs and the differences in the air pressure, different zones around it, you can predict the power output and the performance, and then you can design it much more. The next generation, you can design much more better, right? Uh, yeah, fluids also, like, you have these drones flying around. They also have people do a lot of simulations for the design of the blades and the number of blades you would have and how it would perform, like how high it can fly. Uh, Another thing is fluid structure interaction is like there is okay. This is one example I would ask you to maybe afterwards you should Google and see. This is Tacoma Narrows Bridge in 1940. So it's in US. So it's suffered a catastrophic disaster that one day the wind speed was very high and then it started vibrating. And when it started vibrating, it just broke apart. Like, you can see the videos with some cars would be moving around and there would be some people and they would all be running away, and that happened because there was some phenomena that was not known at that time. It's called as aeroelastic flutter. So when this broke down, a lot of investigations happened. A lot of researchers came and tried to analyze what wrong would have gone with the design of the bridge, and they made a lot of theories. And nowadays, like, we can actually do these simulations uh, for the effect of fluid, like air is a fluid, right? Air is a fluid. So the fluid that flows around it, the air, when it flows around it at a very high speed, yeah, and the this system has some frequency at which it would have some resonance. It would start vibrating very rapidly and it would break. You must have, I think, in your school might have done those uh, simulations, so not simulations, these tuning fork striking. When you strike tuning fork, one tuning fork leads to the vibration in the other tuning fork. Because of they have similar frequencies, it would cause a vibration in the other one, although they are a bit distant apart. So this is also because of you have this structure and then the fluid in between and the structure again over there. So, and the sound wave that transmits from one tuning fork to the other, it causes vibration in the other one if they have very similar matching frequency that causes the resonance. Uh, yeah, also fluid structure interaction can be seen in dams, like if like designing dams or any structure where you have the water and then you want to control the flow of water. Uh, so yeah, you would do some simulations over there, and there are different techniques for simulations. Uh, like this one is fluid structure interaction. They have used these are small particles over here of water that are represented by some small solid spherical bodies. Uh, Okay, now the other thing is thermal simulations. Thermal simulations, like you see the heat exchanger, or maybe also the radiator. I think if you're like in your rooms, you would have a radiator, which would be, especially in this winter time, you would be using it for sure. So there is a fluid, right, flowing inside the radiator. Like there's a water or oil, whatever that is flowing around it gets hot, right, and then when it gets hot, the air surrounding it gets hot, and then there are convection, which flow of air around it, and it carries heat and distributes heat around in your room. And also in the uh, manufacturing of cars, they also take care of these radiators that they would have, like in cars, like the engine gets very hot, especially the traditional IC engines. When they use in a car, it has fuel, and the fuel ignites, and it causes the motion in the piston, and then uh, that leads to the rotatory motion that at the end comes out as the rotation of the wheels of the car, and then your car goes ahead on the road. So in this, you have these engines, and these get hot, and you would want to cool it. So you would have this radiator. That's why you would have seen on the front of the car, like there's a small opening, like the air flows from there, and it cools the engine. So you do simulations for this. So you have this thermal effect combined with the fluid. Okay. And the other thing is like then the chips, electronics, like in your computers or mobile phones, which you're using right now. You would have some electronics chips, and they get hot, right? Current is flowing through it, so electrons are running through them, and their electrons are colliding here and there. There's some friction that a lot of things are happening at the same time. So it generates the resistive forces generate heat energy. Uh, and when that resistor forces are generating this heat energy, you would want to dissipate that heat energy. Otherwise, the system might melt, like and the chips might just melt. So you would want to do a thermal simulations so that that it can cool. Right now, I'm using a laptop, and its fans are running continuously, circulating the air around it, around the chips and all, so that it stays cool and it works properly and doesn't just blow up. So yeah, this is one thermal simulation example. Uh, Heat exchanger, radiators. Um, so okay, it's good, all good, but the question then now would be like, how does it work? Like, okay, it's all good, but like, what is it that happens? So these are the applications that I talked about, like people use in industry. But as an engineer, your job would be to actually make these algorithms and these softwares and solvers that would work properly to simulate things. Uh, or maybe I should say that these are the things that you should be taking care, because there are two things. Okay, I should uh, I should mention that there are two things that you can do. You can use the softwares that other people have designed, which is something you would do if you just go for a master's degree, because this whole computational modeling thing, you start actually using these softwares and solvers from around your third and fourth year of your undergraduate degree or master's degree. Like here in Oxford, it's like 4 year MEng. So in third year, you would learn about, and second year, you would learn about the basics, the theories, the solid mechanics, the structural mechanics, all this stuff. And then in the fourth year in the masters, you would actually start better appreciating the how these solvers and the softwares that people use for simulation, how these work. And yeah, and then if you just graduate after postgrad and then you go to industry, you would mostly be using these softwares and that are already established. And the knowledge that you would have during acquired during your undergrad and master's studies, you would use that knowledge for actually designing these cars, or like whatever you want to design. Like Formula One cars is something like a lot of people do here in UK. So that's one thing. That's one example. Or maybe in aerospace industry, if you go, like the big names are here are UK's like Rolls-Royce, Airbus. Uh, yeah, so you can use them, these softwares and solvers for them. Or the other thing is like, if you go for higher studies, like if you go for PhD, then you can actually go in depth into the mathematical formulations, come up with something new mathematical formulations that you write in the form of algorithms, which would be used as a backend of these softwares and solvers, which the companies use in their design and development. So these are different streams people take depending on their what they like or what are their interests. Okay, so how does it work? Okay, briefly speaking, before 1900s, people were just doing theoretical mechanics, and that still now people do theoretical mechanics. But like somewhere around 16th, 17th century, we have people like Newton, Lagrange, and like all these people who were giving us new theories on classical mechanics. Uh, for example, F equals to ma is the basic equation that everyone studies, right? uh, I'm sure you all know what F equals to ma stands for. But the challenge is that this is a very simple explanation of how any particle would accelerate with time if you apply some force F on it. But if you have some complex randomly shaped bodies, like I have shown, like two potatoes like shaped bodies. So if you have two bodies which are coming into contact and interacting, even if it was just a single body, then you can apply F equals to ma at any particular point inside it, right? This point at any mathematically infinitesimally small point. But the overall body is a continuum, right? It doesn't have, we don't consider atoms actually, by the way, in this simulation so far. We don't consider atoms. We consider everything is continuous, and we just make them in the form of elements, small elements. So we can apply this F equals to ma equation on these elements and then see how it's going to work like. Uh, but yeah, it's very challenging. Theoretically, it was just a continuous medium until like 1900. We don't have elements, all these concepts yet. So what happens now is like you just take any small particle inside it, and you have lots of force acting on it. So there is some complex mathematics that you use here. This is called the as a stress. So you define loading at any point inside the body by a term called as stress, and then you want to predict how the loading would be distributed at different parts of the system. Because if the loading exceeds the strength of the material, that would break, it would fracture and break apart, and your whole system would be breaking up, and you don't want to do that. Uh, there are some analytical or some exact solutions, like just I showed you in the beginning, a quadratic equation. Like you have this ax square plus bx plus c. You have a solution for that, x equals minus b plus minus under root b square minus 4ac whole upon 2a. So just like that, we have solutions to some real problems, but they're very simple. Like you have a sphere, like a spherical indenter, which is pressing against another flat body. Then you can predict that how the loading would be distributed at all points in this material. So you can see that, okay, this is within the strength of the material, like the loading is within the strength of the material, so it can tolerate it. But if the loading is too high, the material would break and would fracture. So you can, based on those, you can make some judgments to make your design more stronger and robust. So around 1940s and 1950s, people started actually having these computational devices coming up, started coming up. Like if you go to any science museum, you must be seeing like around 1940s, 50s, we started having these new calculators, new computers started coming up. Like they were initially very, they could not do a lot of complex calculations. So the initial numerical modeling that we started having in this uh, for mechanics, the formulations were also very, very simple ones. But still, they were good enough. But they were very simple ones. You cannot design very complex systems. But nowadays, we design complex systems. So we have this capability. Like, for example, if you are designing this, this is the blade of the gas turbine engine. And if you want to predict like how if it's in contact with the root or near the root of the blade, how when it's in contact, you would want to predict the friction that is experienced over here when it is like vibrating, and whether it can actually like stay intact over there so that it doesn't really just break off. Because when these blades break off, in the case of these, as I was showing here, like the way you have these when a soft bird, like when a bird hits a blade and the blade just breaks away and it hits the casing. So you want it to just hit the casing, but then you don't want the casing to break, because if the casing would break, then it can hit the fuselage, like the passengers would be sitting inside the plane. So it would be a hazardous situation, like a lot of people would die. You don't want to do that. So certification requirements actually make it mandatory that your this blade should, when it strikes the casing, it should stay inside itself. It should not just break apart the whole thing. uh, yeah, so to actually do this kind of simulations, you would have initially this physical thing, how it's going to be designed. Like, so you design it virtually, you make a design using some computer aided designing softwares like Autodesk and all. uh, and then you have this design, then you make a small sized elements everywhere around the whole body. So you discretize it. What the technical term is discretize, what it means, like you just subdivide it into a large number of small elements. And then you based on whatever the forces you think it would experience, then you would apply all that load on this blade, and then see that how the loading would be distributed at different parts of the blade. At some part it is higher, at red is more high than the blue. So if this is more high, so you know that this part is more critical. You need to put more material over there so that it can take loading better, so that it does not break. Um, yeah, so the distribution of loading is important, especially if you have contact between solids. Uh, yeah, so nowadays we can design complex systems. So these computational model, briefly, like when you go for numerical simulations of these structural mechanics problems, you would have some geometry. Like here, like you have this geometry you have designed for the blade. Then you would throw in all the properties of the materials that are used in the geometry, all the mathematical models of the physics. Like the F equals to ma is one thing that you guys all know. There are some more complex things as well, which you throw in all this geometrical description of the model. And then you put in what that, okay, what are the initial motion, how the blade was moving, and how it was supported, and what kind of load was it getting, how was it distributed, what was its the intensity. And then you have this initial problem description. The top part is just the problem description, and then you use that initial problem description in your computational model, which would be a simulation software. And then you can use that for solving it, and then you got a solution based on your computational model. And if your solution is good, it is then going to give you a lot of confidence in your design. Then you can go and actually make it. So how does it work like? Okay, briefly, like if you have this CAD model, you make a large number of elements. These are called as finite elements. You define the geometry, you apply the loads. Boundary conditions is just like saying that like where it is supported, how much load is applied at what part of this design, what are the material properties, and what is the desired output. Like you define that. You tell the software that what you actually want to see. You want to see the distribution of the load, how the different particles are displacing, how much, what's the displacement, velocity, acceleration, all these things. So you just tell it, and the software would then, when you have given all this information in a correct order, it would give you a solution. So again, some other examples of just showing like how this might look like. If you have some geometry, you make a mesh from it, and some more just geometry and mesh. You can have these elements of different shape and size. Like, this is a tetrahedron, and you can also, like I was showing, like you can have a hexahedron, you can have a tetrahedron, you can have prisms. So these are all actually based on some physics, and there are a lot of complicated things which I would skip for you to study in your master's or PhD if you want. But yeah, so this is how computational mechanics is like. Okay, a simple example: if you have just this system over there that you can see here, there's a concept that you would apply some load here, some support here. There's a let's say a screw, you're tightening a screw. You applied some load here. This is a material made of steel. Then you would these what you are seeing is one message stress. Technically, it's called one message stress, but what it is showing is the distribution of the load. So you can see that this red part is going to be more vulnerable to breaking, or this would be the first part to break if the material is not strong enough for this particular shape and size. So yeah, so you can see it like how it will work. And like if you have complex systems like cars, like you would make the mesh, and then you would do all this process that I just explained, and then use the put the car in the virtual space to see to show you how it would look like when it breaks. Some other examples can be like biomedical applications, like if you're making these biomedical implants, like a bone, like if you're going to they put in biomedical implants, so whatever material that they are using here, then they would want to simulate it to get a good idea of how it would look like. So yeah, these are different kind of elements you can use, and like whether you are doing a 1D, 2D, or 3D systems. And then physical phenomena, they would have some mathematics. I've tried to show some mathematics to you over here, but these are very simple mathematics. Whether it's a solid problem, fluid mechanics problem, thermal conduction problems, diffusion, like heat is diffusing. Okay, and it's electrical conduction. Uh, so these are all just telling you that you have some mathematical model, you make some system of equations, some linear equations, and then this is what is going to give you your actual problem description, and then you solve it. A simple example can be like if you have a bridge and you have lots of bars over here, what you do is like each bar, you have some forces acting on its ends. So you make this system of equations, just a matrix and equations. And yeah, this is just for you write just for one element, that if these are such and such forces acting on it, and these are the stiffness of the element, like just like the spring stiffness, and these are the displacements. Then what you do is like if you just like, let's say two elements in a system, this is like, let's say this is the only system, two elements, then you would have forces acting on the ends of it. So you would make a system of equations, and this u1, u2, u3 are basically telling you the displacement of this 1, 2, 3 points. And then based on whatever forces that are acting on this system, you can predict the displacement and find out the displacement of the entire body. Okay. Okay. So these are just some suggestions for you to look into. It's a lot, and I could not pack everything in 1 hour. So I just left you with some things over here you can to look into afterwards. As this is one simulation software which is free to use. Is go on this website. You can just log in and start simulating just to see how it looks like, and some theoretical stuff that you might want to look and Google and like look into, like what they study in those things, like particularly for computational mechanics simulations, and some softwares for designing and simulations. Okay, this was a quick tour of what the computational mechanics and computational modeling is about. Uh, I hope you guys got something to learn about here, this field here, and I'm open to any questions that you may have.